Hello, everyone. I'm so excited to have everyone over here. We have Eli and everyone present. We already have about 100 people joining in, and I'm really excited to kickstart the entire Starknet House session. So Starknet House started in December when a few Starknet ecosystem people gathered together and thought that there might be an exciting place where we can actually create an educational platform where we can teach people how to deploy a contract on Starknet and also introduce what it means to build on Starknet ecosystem. So we're kickstarting this 11-week journey, starting with Eli talking more about what exactly is Stark and Starknet. And I'm very excited to kickstart this with Topology. My name is Kan-Ho Kim, and one of the co-founders of Topology. And without the help of the sponsors listed over here, this event would never have been possible, especially thanks to Yuri and Eli from StarkWare, Argent, Bravos Wallet, Brick NFT, Matchbox DAO, Jedi Swap, Lyra Finance, and Door Labs. With everyone's support from the ecosystem, this program has been possible. Just for a little bit of logistical and housekeeping stuff that we need to do, there will be a workshop run by Only Dust team in Gather Town. Thanks to Gather team, they sponsored the event. There will be a workshop where you can learn how to deploy a contract on Starknet from 0 to 1. We'll share the GitHub and also how to start these workshop on our Discord channel. Next, all the Q&A sessions related to our workshops and the Starknet House will be available at triality.org. This is an awesome project where you can ask questions and mentors from our program can answer any of the questions that we feel relevant to the program. And at the end of the session, we'll ask everyone to fill out an attendance sheet, and you need to fill out 7 out of 11 sessions attendance in order to attend our online Starknet Hacker House, which will happen at the end of 11 months. And without further ado, I want to introduce Eli and talking about what Starknet is. So thank you very much, first of all, for coming attending this and helping everyone over here to let us know what ZK Stark is.
Thank you, Kun-Ho. Can everyone hear me?
Yes, I can hear you.
And let me now try to share my screen. Can you see the screen share?
Yes.
Very well. And just Kun-Ho, for how long should I speak before we go to Q&A?
30 to 40 minutes, but if there's anything that you want to talk more, we'd be happy to spend more time.
Okay, so 30 to 40 minutes and then Q&A, right?
Yep.
Okay, terrific. So I'm very excited to be here. And again, thank you so much, Kun-Ho, and also Guilty Gyoza and Topology and all the other organizers of this. It's just so exciting and thrilling to see an ecosystem starting to be built and being completely independent. This is exactly what we had hoped for, and it's now materializing. It's just so much fun, and it's such a joy to see. So without further ado, I would like to first of all tell you a little bit about ZK Stark's math prehistory. This is not about Starknet and how to program or deploy on it, but it just gives a little bit of context for where the technology came from and how it came about. So I hope you'll enjoy this story, or his story. So let us start with the famous PCP theorem. And one way to think about it is, we all know that polling or sampling is highly effective, surprisingly effective. And mathematically speaking, when you poll an election, the margin of error is independent from the sample size. And that is actually quite amazing, right? If we would like to predict who will be the winner of the next election up to some small error margin, all we have to do is pick, let's say, 1,000 people, and we'll get a margin of error that is roughly 3.1%. I just copied this through some calculator of margin of error. And the amazing thing is that if the population size is 1 million, it's enough to pick 1,000 for this margin error. But if you also go to a population size that is, I don't know how many zeros there are there, and you only sample 1,000 people out of them, you will still get the same margin of error. So the sample size is what determines the margin of error, not the population size. Now, the PCP theorem and this whole field that I'm now describing, and the field that is the predecessor to Stark's, has shown an amazing analog of this, which was also extremely surprising at the same time, that the same effect holds for mathematical proofs and for validating the integrity of a computation. So what do I mean the same holds? If you want to sample a computation or a proof and know to a high degree of certainty and a small margin of error whether this computation was done with integrity, whether this proof is correct, well, the margin of error depends only on the sample size, and it does not depend on how complicated or long is the computation or the proof. So this is absolutely mind-blowing. Sometimes it's described as you can check the validity of any proof, the integrity of any computation, by reading only a small number of bits from it. And the number of bits you need to read will determine the margin of error, and the proof size and the computation size matters not at all. And this is absolutely mind-blowing. Now, there's a small caveat. Of course, you always need to read the fine print. The fine print here says that you can do this only as long as the proof or the execution trace of the computation are written in a certain nice format. So let's talk a little bit about this format. And this is a theorem that was well known in the 1990s. So we're talking about more than 30 years ago. So here's one example of a phenomenal paper discovery from the early 1990s. And I'm just reading here one sentence from it. So this is a work by a brilliant mathematical work by Babai, Fortnow, Levin, and Segedy. And here's what it says. It says, in this setup, a single reliable PC can monitor the operation of a herd of supercomputers working with possibly extremely powerful but unreliable software and untested hardware. Now, if you think about the way Stark's work today, they are an implementation of this vision from the 1990s. In our setting, a single reliable smart contract does indeed monitor the operation of a very large computer, the prover, the processor of Starknet transactions, and you don't care at all if that supercomputer is operating on powerful but unreliable software or untested hardware. It doesn't matter. All you need to do is trust the smart contract or this single reliable PC. So this was known in the 1990s, and you may ask, okay, well, where was it implemented? Or rather, why wasn't it implemented? And the problem was that if you take this theorem and try to implement it, there were just not enough atoms in the solar system to write down a proof in the nice format that would allow it to be verified in this efficient manner. Okay, so this was a theoretical result, but one that had no concrete efficiency, not something you could use. Okay, the way I got into this whole area was that initially I was involved in some mathematical work that shortened the length of these proofs. In particular, something like 15 years ago, we made significant progress with Madhusudan, and also this was building on other works with others. And what we described, what we got there was that we found a format that if you write proofs or computations in it, there are just enough atoms in the solar system to write down a proof that can be verified via this polling system. Okay, this was still not good enough because we need something more efficient. And what happened was my colleagues and I continued working for a while, and this is all mostly pure math. And we came up with new models like interactive oracle proofs. So this is work with my co-founder at both Zcash and StarkWare, Alessandro Chiesa and Nicolas Spooner. We found the Fry protocol, fast read Solomon interactive oracle proofs of proximity that made things even more efficient. And finally, culminating with a full-blown description of a Stark. And you could summarize it as saying this construction shows a way in which you can write the proofs so that there are enough atoms even on your laptop to write down that proof so that it can be verified efficiently. So this was around, took me like 15 years, not just me, but many others as well. A lot of works there. So this is sort of the background, the mathematical background and the foundation on which StarkNet and the Stark proof system and Stark systems are built. Now, what is it exactly from a mathematical point of view that we achieve in a Stark? So I want to explain what S and T mean in a Stark system. So if you have a proof system comprised of the prover, this is this supercomputer operating off-chain and submitting proofs to the verifier. And then you have this very weak smart contract that is the verifier that verifies integrity of computation. So you can say that such a construction, such a pair, a prover and a verifier, form a scalable system if you have two properties that happen simultaneously. The first is that the proving time scales nearly linearly with the time of the computation that you're executing and proving. And simultaneously, the verification time scales exponentially faster or exponentially better than that. So verification time scales like the logarithm of the computation. And again, T is the number of steps that you would need to naively run the computation on your input. And it may include all kinds of auxiliary inputs, like which we like to call the witness. So passwords, private information, and so on. So that's the S. A proof system is scalable. If the prover is nearly as efficient as one can imagine, you can't do better than T steps. So we want it to be T times a very small logarithmic factor. And at the same time, you want verification to be exponentially faster or logarithmic in T. We also say that a proof system is transparent if it requires no trusted setup, no toxic waste. All you ever need on the verifier side is just public random coins. So if you have a system that satisfies these two properties, and I don't want to explain what the ARK means, if you have these two properties, then you have a Stark. Now, in particular, notice there's no trusted setup, and whatever keys you do like to generate should be generated in time that is polylogarithmically in the size of the computation. Or stated differently, as you scale to larger and larger batch sizes and larger block sizes, you do not need the smart contract verifier to do a lot of work. All you need to do forever is just a logarithmic amount of work and the amount of computation being processed. So all of this is very nice and dandy theory, but where would you apply such a theory? And again, I want to talk a little bit about ZK Stark usage prehistory. So this is a sort of product market fit. If the product is the ZK Stark system, where would it find a fit within the world of commerce as we know it? So, well, you know the answer, right? Bitcoin is really this amazing revelation, and it is the market that dearly needs things like proofs. And by the way, even though 14 years have passed since Bitcoin arose, today, the only realm in which general purpose zero knowledge or validity proofs are actually needed and used in products, the only worlds are the worlds of permissionless blockchains. And we'll get back to this a little bit later. You could have hoped or thought that by now, banks and healthcare systems would be using this. Well, that's not the case, and there's good reason. So anyways, without Bitcoin, I would have a very hard time commercializing this marvelous math and technology. So thank you, Satoshi, for one more thing. that you did. I would just want to tell you a little bit about my personal red pill moment. So I was doing academic research. I knew very little of Bitcoin, but I did happen to stumble upon, or rather I decided to try and, go and present my work, not just to academics, but also to the attendees of the Bitcoin conference in San Jose. And for me, that is the moment of eureka and the place where I swallowed the red pill and where my life changed. I've been by then building academic proofs, even in code, since 2008, and doing the math around them even earlier, since 2001. And when I was peddling my work and showing it around to academic researchers, which is the world I was inhabiting at the time, people would be sort of glossy-eyed and would ask, why, who cares, why are you implementing this in code, who would like to prove what to whom? And then when I attended the Bitcoin conference in San Jose, the Bitcoiners, at the time there was really only Bitcoin in 2013, this was even pre-Ethereum, only colored coin and things like that started showing up. But so the Bitcoiners came up and they didn't ask why are you doing this? They asked, where's the code? We would like to use it tomorrow. And here are like 5 different things you haven't thought about that we want to use it for. And I was just completely blown away, and basically started working with my colleagues very hard on, the merging of blockchains and proof systems ever since. Wait just one second. I just want to make sure that I'm not, that I don't have any, okay, sorry. Just one second. Okay, I hope there's less of an echo now. Kunho, can you hear me well, or do I have some echo phenomena or something?
It sounds fine. A little bit of echo, but I think it's largely very okay.
Okay, sorry. Okay. So this was my own red pill moment. Okay, thanks, guys. So I'll just continue. Now, the next step for me and my colleagues was publishing a use case in which we showed how to use the zero knowledge property of proof systems in order to solve the privacy problem of blockchains. And this was the zero cash paper, which then led to the Zcash cryptocurrency, of which both Alessandro and myself were co-founders of. And this gave further credence to the potential of this weird mathematical theory to do good things within the world of blockchains. So after the red pill, the zero cash academic paper, and Zcash, I tried to commercialize this technology by other means, but actually failed. I did enjoy the process and I learned a lot. So if you're, in the throes and of trying to commercialize and have various issues, well, not all is lost. I hope you will learn something, even if it doesn't quite work out. Then I already told you about these math breakthroughs that we were very excited about, because we saw that they are really the missing link between the theory that was impractical and making this completely practical. But these breakthroughs were not well received within the academic world that I was inhabiting at the time. So, for instance, the Fry paper was rejected from 3 conferences and was finally accepted, not to the top tier, but to one like lower tier conference, and no one really attended the talk. Stark was rejected from 4 conferences, finally accepted to Crypto, which is the leading conference, but a lot of agony till that happened. And there were a bunch of other papers that I still think are very interesting in the context of practicality of this technology that were rejected so many times that basically I just gave up. Now, why? Well, it was part of this process of, something that is too practical for mathematicians and theoreticians, but also too theoretical for practitioners. And there's this very nice quote that was referred to me by Professor Gil Segev, that goes back to Moni Nao, who was a famous cryptographer, and also the original proof of work comes from a paper of him and Cynthia Dwork. And he said, well, if your paper is viciously rejected and one referee says the result is not new, another one says it's not correct, and the third one says it's not interesting, then you're probably doing something interesting. And I remember Gil telling me this, and then a week later, I forwarded the reviews of yet another rejection of the Stark paper, and I said, look, here's number one, he's saying it's not new, and number two saying it's not correct, and number three is saying that it's not interesting. And he agreed, this must be something interesting. Anyways, so meanwhile, and thanks to Satoshi and blockchains, in blockchain world, no one cared about these things, and everyone was very, very enthusiastic about the potential of such proofs. And when we came out with the ZK Starks and told them about the breakthroughs, so this was very, very well received. So we co-founded StarkWare in 2018 with Alessandro Chiesa, Uri Kolodny, Michael Ryabtsev, who was my PhD student at Technion, and we got pretty immediately, this was the era of ICOs, even though we didn't contemplate doing an ICO, we got pretty decent funding from the start. And by now, with the Series D just behind us, at a valuation of $8 billion, at least it seems that we have smooth sailing so far. Not touch wood. I hope it. Don't want to jinx it. Now, at launch, another interesting thing is that many of the crucial technology components were still missing. For instance, we didn't have results such as deep fry, tight soundness analysis. All of these things are now a crucial part of the efficiency of the Stark system. We didn't have the system accessible, not to our engineers and not to anyone else. We didn't have Cairo. We didn't know it will exist. We didn't have a system. We didn't have a business model, and so on and so forth. We didn't know what the product will be. But we had a very deep conviction that this is the right technology. It is future-proof, it's post-quantum resistant, it is most scalable. It is really the right tool to address the pressing problem of scalability. And by the way, when we launched and we said we're going to solve scalability, everyone said, which scalability problem? There is no scalability problem in blockchain, so why are you doing this? Our answer was, guys, if blockchains are going to win over the world, and they must win over the world, there will be scalable, and there will be congestion, and we have the tool that can solve it. Anyways, so now we're done with the math part. Let's talk a little bit about what StarkWare, X, and Net are. So StarkWare is a company. Its mission is to bring integrity to computation through math. Its pedigree is something we're very proud of. We invented ZK Starks, Fry, Cairo, the Sharp shared proving system, the Validium data availability model, Volition, we can add layer 3, and so on and so forth. We have 80 plus team members. We've raised $260 million of funding. And what are we doing? Or why is this technology needed where it's needed? So here's a paradox. Bitcoin was launched in 2008 and Ethereum was launched in 2015. So why are they so slow compared to Visa, for instance? By the way, Kunhu, I see that there are some comments on the, can you hear me and see me okay?
Yep, we can see you here fine.
Okay, and the echo is not too bad?
Not too bad at all.
Okay, and I think the dog stopped yapping, right? So we're also good there. Good. It's okay, maybe he's listening in or something. or either that or I am barking even louder than him. So, okay, we see the screen, we can't see you. Okay. Let me try to stop this video. and start again.
I think we can see you. I think it's that particular person's setting.
Okay.
Yeah.
Okay. So I'll continue. Okay. So why are these systems so slow, even though they are based on new technology? By the way, Kuno, I see that there are some questions and answers. So if you want to stop me, I mean, this might be a good time to stop and answer a couple of questions to your discretion. I haven't seen them. Do you want us to go on or to stop for a few questions?
I think we can go on, and then we can have a full Q&A session. Yeah.
Okay. So I'll go on for, I think, 15 more minutes, and then we'll take some questions.
Yep.
Okay, so back to this paradox. Why is this technology launched so recently? Why is it so slow compared to much older technologies like Visa? And the answer to this is all about computational integrity in your basis of trust. So there's this beautiful quote by C.S. Lewis: integrity means doing the right thing, even when no one is watching. And if you think about financial transactions or about data that is very important, forensically, medically, or financially, how do we know that computations and data is actually handled with integrity? So here's the conventional world with banks, healthcare systems, governments, and so on. We delegate the process of accountability to some, we delegate the process of accountability to some trusted parties. And these are accountants and auditors and so on. And they check on our behalf that the system operates when we are not watching. So just one second, I just want to maybe try and make this thing. Is this better now? Yeah, I think now there's no, okay. Okay.
Much better, yeah.
I hope this solves the, yeah, sorry, I was just, okay. So this is the conventional system. And how does the new system operate? Blockchains. It's about inclusive accountability. Each and every one of us is invited to run a node and verify all transactions and not trust anyone else. And it's really a beautiful, democratic, empowering principle, inclusive accountability. However, you sacrifice privacy and scalability. If you see all these little transactions, now each one of us has to verify all of them. So first of all, we get to see all of them, which means that now, we lose privacy, but scalability is compromised because if we go and ask everyone to increase the capacity, the bandwidth, then many people are going to drop off or not have enough funds to go buy a bigger computer. And that's bad. And because we want to maintain inclusive accountability and make the system always available for verification by all, we are not willing to increase bandwidth and capacity. So it's because of this that this new technology isn't as scalable and doesn't have as much throughput as Visa or banks. So here's the current state of affairs. We are offered to choose between two worlds, one in which we trust the central party or to trust its big computer, and the other in which we all run smaller computers and check everything. Now, of course, you get much better scale if you trust this big computer. So the problem is that in one case, you have public transportation, but you might worry whether the driver is someone who has integrity and can be trusted. And on the other hand, you have a lot of, private cars that are clogging up everything. So that's the situation now. Now, what can you do? Well, one thing you could do is increase the scale. For instance, increase the gas or block limit and have more lanes to your highway. But this does not work so well, and it gets clogged again and again. And if you think about it, I mean, what happened with blockchains is that, yeah, block size has been increased, gas limit has been increased, and it all gets congested once more. And also you have another effect, which is that people start dropping off and you get a system that is more centralized. You can't increase this too much. Another option is to use fraud-proof rollups like Arbitrum and Optimism, where you're basically saying you do not need to go and purchase a bigger computer. There are some economic incentives that you should feel comfortable trusting, and they will incentivize some people to run big computers on your behalf and find out if there's any error. But still, you're moving down this slippery slope towards a more centralized system, and you might wonder whether the economic incentives are such that those parties are really doing what they should be doing on your behalf. What we are offering to use is to use this math-based approach of ZK Stark proofs, which is akin to having public transportation, but one in which you know that the driver can be trusted and the driver is operating with integrity, because integrity is forced by math. And that's our approach. There are, of course, other approaches to these validity rollups, ZK Sync, for example. And we think that this is the optimal way and the most future-proof way in which you can both get the scale that you need without needing, so you get public transportation, but the driver has integrity. So what are proofs? Here's an example of a proof. It is a proof of a statement. The statement is that if you sum up all the items and tally them up and add the tax, you need to pay $89.50. The prover is the restaurant owner. He's the one who generated this computation. The verifier is the customer. And how will the verifier check this proof? Well, by naive re-execution. So this is a very old form of proof, and it works pretty well. However, it's not scalable. So ZK Stark proofs are a proof. They are a little bit like these receipts, but they can offer you zero knowledge, which means you can blind some of the items and still know with near certainty that the result is correct. And they offer you scalability, which again means that verifying the proof does not involve rerunning the same computation that the prover did, but rather something similar to polling or sampling an election result. You just need to read a few locations, and based on this, you can get to know with a very high degree of certainty that the whole computation was done with integrity. So once we have this, the way we can operate the system is have a lot of transactions sent to the prover. The prover will generate a proof. The prover need not be trusted. This is one of those supercomputers that may be running on faulty hardware and untrusted software. It doesn't matter. All you need is for the verifier to be run by everyone. So you can have inclusive accountability, having everyone run verifiers as smart contracts, and you can have integrity at scale by having provers that need not be trusted, processing transactions and submitting proofs of integrity whenever they update the state. And this is exactly how we work. And it has great advantages. For instance, if you use the blockchain, if you use a block of Ethereum to mint as many NFTs as you can fit roughly 150 of them within. Whereas for one of our customers, Immutable X, we regularly generate proofs that currently fit 600,000 NFT mints, and one block can easily fit inside it 3 proofs or more. So using this technology, you have increased by tens of thousands the capacity, the throughput of the system without requiring the validators, the nodes, to go out and upgrade their laptops to be bigger computers. Now, we took this technology, this math technology that we invented and then honed, and we put it inside two layer 2 offerings. One is a standalone offering called StarkX, and the other is Starknet, which is the system that is the main, course of this particular event. So I'm not going to talk a lot about Starknet. StarkX is by now pretty much the largest the largest L2 in terms of many metrics that you care about. Cumulative trading has settled more than $600 billion. The number of transactions exceeds by far all the other L2s combined. There were weeks, or at least 1 week, during which we processed more transactions than all of Ethereum. And it took us gas that was less than 1% of Ethereum's gas during that week. We minted more NFTs than any other blockchain, L1 or L2. And a single transaction is lower than 500 gas, and it will likely go down lower as we increase scale and capacity. So 500 gas per transaction is not the end of the story. And we have, we could never have done this without all of our partners, DYDX, Rare, Immutable, Diversify. There's also Seller by now, and there are more that are going to be launching soon. All of this is StarkX. Starknet is like Ethereum. You can deploy smart contracts to it. It allows you general computation. You can post things. It's a layer 2. Whereas in Ethereum, you send transactions to the mempool, and there's a single miner at a given time that selects them and processes them. And then everyone needs to re-execute the new state. In Starknet, the transactions go to the mempool. They go to a sequencer, and then it goes to a prover that executes and proves the integrity of all of these computations. And then what you broadcast to the network is just the state diff and a proof of it. And now the Ethereum nodes don't need to re-execute all of the transactions. They only need to update the state and to verify the proof. So where are we now? We're now just beginning of June. Starknet Alpha version 9 has been released. It includes fees in it. The bridge has been turned on. We are in an alpha. And basically over the next quarter or two, we are improving the throughput and performance. And right after that, we'll be heading towards decentralization. And we're going to have a lot of exciting news and announcements throughout the summer about our plans for decentralization. So, stay tuned for that. The Starknet ecosystem is thriving, right? I see there are 114 participants right now. That's one example for that. So there's growth in every important metric. And this is just absolutely exciting and surprising. We didn't think we'd get so much warm reception so early in the game. So this is really, really warming. And of course, Kunho, Gilti Gyoza, the Topology team, and many others that are attending and sponsoring this event are, of course, the leaders of this effort. There's a bunch of worldwide events. For instance, the first Starkathon we did in Amsterdam, electrifying atmosphere. People coded for 24 hours throughout the night, more than 40 projects, amazing mentors, really beautiful thing to see. There's, of course, unforgettable swag, which is the real reason people are coming for. So here we see Tom, who is both our presenter for swag, but also, as a side job, is the product lead for Starknet, displaying this unforgettable swag. And there's a whole bunch of activities in which we'll be participating and others will be doing. Activate Miami just happened, ETH Prague taking place next week, Blockchain Oracle Summit, ETHCC. I think it's going to be a really, really exciting event. We'll have hackathons around that. BITL Asia, ETH Seoul in August, ETH Latham in August, Sanford Blockchain Week in August, and so on. There's a lot of tooling, full nodes explorers, JS and Python packages. You can install a full node with a click on a Raspberry Pi, and a bunch of applications, games, NFTs, and all kinds of smart physics and financial simulations, like the stuff that Topology is spearheading. So that's the end. Time for questions. Thank you very much.
Wonderful. Thank you for your wonderful talk. I'll hand over the Q&A session to Guilty Gyoza.
Hello.
Yes.
Hi, Ali.
Hello.
Just want to say upfront before the Q&A that I think to us, the invention of Stark is analogous to like 100 years ago when the theory of special relativity was published. So we're just really fortunate to be able to build on this technology and in this space. I'm Guilty Gyoza. I am the other co-founder of Topology. Let's start Q&A. So I will go over the 5 questions currently in the Q&A panel, followed by one question I saw in the chat. That's okay as an order. Oh, I see questions are still popping in, so I'll do a FIFO manner. Let's start with the first question asked in the Q&A. Okay, this is a long one. So can you talk about Starks versus Snarks from the perspective of 3 perspectives? Number 1, time to finality. Number 2, throughput. And number 3, gas fees. And in particular, Starks are usually called quote unquote more scalable, yet in some studies, they're shown to have higher verification costs and therefore higher gas costs anticipated for end users.
Yeah, I saw some of these research works, and I think they miscalculated. When you talk about gas or scalability, what really matters is amortized cost per transaction. That's the main thing you care about. We are, to the best of my knowledge, the only system in production that is offering its users L1 gas cost of less than 1,000. And by the way, in some cases, for instance, when we mint 600,000 NFTs within a single proof, actually the amortized gas is less than 10 gas per NFT mint. So to best of my knowledge, there is no other system in production that comes near to this kind of scale, okay? And this is in spite of the fact that a single proof of ours, verifying it on Ethereum, costs several million gas, right? So if you look at the cost of verifying a single proof, yes, it costs more, but the amortized cost is much lower. So here's an analogy. A car, let's say a large car, a van, okay? It consumes less gas per kilometer than a train, obviously, right? A train consumes much more. But of course, a train is far more efficient in terms of gas usage, right? Because the amortized cost per passenger, which is really the only thing you care about, is way lower. So that's the right comparison. And again, I don't know of any other production validity proof system that gets to less than 1,000 gas, and we get to less than 500 for very complicated transactions, and even less than 10 gas per transaction for things like NFT mints. Throughput, again, I don't know of any other system that can process, just to give you an example, in a single proof, we put upwards of 12,000 settlements of DYDX transactions, and each one of these transactions is highly complicated. I am not aware of any other proof system today in production, or even, you know, coming close to that, that handles the kind of business logic at this throughput and for such a low amortized cost. Again, 500 gas per trade of DYDX. So, but you know, I don't know what papers you're referring to, but I have seen all kinds of papers where, how should I describe it? You know, if you're an academic and you got some result that you really like, you can always find the right metric to present it as the very best thing according to that metric. But I think the metrics that matter to users, I think Starks outperform everything else today.
Wonderful. I want to ask a very quick follow-up question, which is perhaps proving time, proof size, verification time, etc. These are non-ideal metrics to discuss between these systems. So what would you propose for better metrics?
No, first of all, I think they're all very interesting metrics, but I can say last time we measured the Stark prover, when we did an apples to apples comparison, you know, like the same number of cores, same roughly type of computation, the Stark prover on the ETH Stark open source system was 20x faster than the second fastest prover out there. This was a comparison we did, I think, 3 years ago. We haven't looked at it recently, but at the time it was 20x faster. It also had, you know, the most scale. Verification time of the ETH Stark statement was under 3 milliseconds on a single core, which is, I think, comparable or outperforms, you know, the very best SNARK verifiers. But even if not, I think they're all, you know, comparable verification time. There's one metric in which SNARKs beat Starks, and that is the byte count length of a proof, right? So SNARKs famously go under 300 and sometimes under 200 bytes per single proof, whereas Starks are in the 20 to 100 kilobyte size proof. But verification time is similar because it's a much simpler computation for Starks to verify.
Beautiful. For time's sake, let's move on to the next question. Again, from anonymous attendee. Why is Starknet built as a layer 2? What modifications will be needed for it to exist as in layer 1 directly?
Yeah, terrific question. Okay, you know, my Twitter handle says I am a ZK Stark maximalist, which means, let me spell that out. I believe this is the right technology. Everyone's going to use it. So just like the EVM is the standard that all chains afterwards have used, so I'm very confident that ZK Stark with airs and fries and Cairo and the Starknet standards are going to be something that everyone accepts and uses, all blockchains. Now, when we are very, so you know, we're Stark maximalists, but we're also very practical in asking ourselves, where is the very best first place to deploy this technology with a minimal amount of complexity? And the first answer was the Stark X system on Ethereum. Ethereum needed the scale and had the ability to deploy a verifier smart contract. I would have loved to deploy first on Bitcoin, but you know, for that you need the Bitcoin community to accept some Stark opcode or something. So just practically speaking, this was the right first system to deploy on. So that's the short answer to that. Wait, I just want to make this thing a bit quieter. And then to make such a thing in L1 is a very complicated, it would add to the complexity and add to the timeline, because you now need the state and the consensus mechanism of an L1. And we much rather prefer on offering the maximal value that we can to the system that needs it most, which is Ethereum right now is an L2. So that's why we're going with an L2. It's a lot of work to make it an L1, and it's not something we're currently thinking of.
Great, thank you. Right, next question, again from anonymous attendee. It's about layer 3. There are a lot of companies looking to develop layer 3 rollups on top of Starknet. So what would be your recommendation to them in developing a prover? Is it viable to develop their own prover, or should they wait for Starknet's technology to be licensed for this kind of use?
So, okay, I would say, this is what I would say. If you want to focus on the product and making it a layer 3, you're probably better off putting your effort in just the product. And there will be provers out there that you can use, released both by StarkWare and maybe by others as well. So I think it would be better for you to do that. If, however, you either want to have full independence or you want to be in the business of generating provers, because this by itself could be highly interesting business case, as infrastructure down the line, then yes, please go build a prover. But I would recommend, especially if you're a small startup, to follow what we have followed and basically try to do one thing very well and not, just like I answered, why are we not a layer 1 and a layer 2 is because we'd rather take the scaling technology offered by Stark and put the minimal amount of effort in which we can now deploy it. So the same logic would say, if you want to be an infrastructure, in the business of generating Stark proofs and Stark infrastructure, yes, do that. That's a really great idea. And talk to us. We'd love to help. If you want to build an L3 for something like DYDX or a game or NFTs or something, I think you're better off focusing just on that. There will be provers that you can operate later down the line. That's my recommendation.
Great answer. Thank you. I think we have a rough cutoff time in about 10 to 15 minutes. And so for fairness, and also fortunately, the questions and messages are timestamped. So I will refer to the timestamp and follow that order. So
okay. And I'll just answer very briefly.
Great. Yeah, that will be helpful. So next question from Stephanie. The proof verification time provided by StarkWare is slower than an approach with Plonk, and the proof size is bigger. So do you think it is a hurdle or an advantage?
Again, what is
it's in a chat. This is not in the Q&A, but
okay.
Yeah.
So what is it? Time, so what is it as? The verification time is?
Verification time of Stark is longer than Plonk and proof size bigger. What do you think?
Okay, so I think that the verification time is not longer. It is either comparable or shorter for Stark, but they're all in the very, in the sub-millisecond. It is definitely true that for Plonk, the proof size is shorter. But I already discussed this earlier. I think it's like, right, a large van is much smaller than a train. But when you talk about scalability, and also a large van consumes less gas than a train. But a train is far more efficient. So the analogy is a Plonk is smaller. It's like a van, but it can fit, practically speaking today, it fits far less throughput than a Stark can fit. And hence the amortized gas per transaction is actually lower in Starks today, to the best of my knowledge.
Great. Next question again from Stephanie. What is your vision in relation to a specific language like Cairo? Wouldn't that be a constraint to grow the ecosystem?
That's a very good question, and I don't know. Okay. You can ask the same question about Solidity and and Ethereum. When Ethereum came along, everyone understood that there are actually amazing programming languages out there, right? Python, C, Rust, whatever. The reason Solidity caught on was because it is the right language for this specific model and constraint system. So Cairo is just another iteration of this. We didn't want to, we would have loved to just take some standard, well-maintained programming language and generate Starks for that. But for the when you come to build very scalable systems with all of the algebra and the complexity and so on, that's the reason you want to work with things like felts, with very small, and very simple machines, so that you can fit more. So I don't know what the future holds, but I do believe it's a very reasonable approach to say, since we have a different constraint space, we are better off devising a programming language that addresses that, even though, of course, there's the downside of it being a new framework and, maybe it's not the right approach. And I just want to say that most of the other teams out there are actually working on the other approach, which is to take some model, let's say a ZK EVM, to take the Ethereum virtual machine and build like a Plonk or a Snark or something for it. I think our approach is better, but time will tell.
Great answer. Next question from Tel. Starknet has a ZKVM and is planning on decentralizing the sequencer. So what is StarkWare's timeline on this, and when can I run a full node?
I think you can run a full node now, right? Just I know I'm running a full node, so you can run a full node now. Decentralization and releasing code for running provers and sequencers, I would say we're 9 months to 1 year from that happening.
Cool, 9 months to 1 year. Next question from anonymous attendee. Can you talk about the roadmap for Cairo and other high-level Stark languages?
So the roadmap for Cairo is that, first of all, there are constant improvements in the language. There are a number of transpilers and compilers being built and improved, most famously the Warp one from Solidity, but there are others. Independently from that, we will be initiating a process of creating some version of a higher level version of Cairo that will make programming easier and better, and will basically compile naturally into Cairo. So we'll definitely see evolution on all these fronts.
Beautiful. Looking forward to that. Next question. Is there some formal verification with ZK Stark?
Formal verification of or with?
Well, I think the question is with, but we can go with off.
So there has been one publication that uses the lean automated theorem prover to prove the soundness of the air of the set of polynomial constraints of the Cairo virtual machine. And there are follow-up works being done right now by Leo Goldberg, and who's co-creator of Cairo, and also was co-author of this one, lean work. So there's ongoing work there. If you know the field of formal verification, then you know that it's very, very hard to formally verify complicated statements and proofs. So that's the reality.
Great. Next question from Mohammed. Is the Stark math and innovation patented and exclusive to StarkWare, or there will be other layer 2 implemented with the same math?
That's easy to answer. We have filed no patents, period. So all of the math has been basically published, and yeah. So no, StarkWare has filed no patents to date.
Cool. Moving on to the next question. and I think this can be short. What are the differences between StarkNet and StarkX?
So StarkX is a standalone system that supports a particular customer doing one specific thing, like DYDX has a StarkX, the Mutable X has a StarkX for NFTs and so on. StarkNet is like Ethereum. It's it's a general purpose. Anyone can deploy permissionlessly transactions to it and smart contracts and so on.
Awesome. Next question from Eshwar. Thank you for the wonderful introduction. How do we stand with respect to other ZK projects on various ecosystems and adaptability, like A0, Monero, NYM, etc.?
So I confess it's very hard for me to keep track even of what's going on at StarkNet. Seriously. So I have very little time to track what's going on in other projects. One thing I can say is that there are already people writing libraries that can verify other cryptographic primitives on StarkNet. So at least one way of this bridging of like proving on StarkNet that some other cryptographic thing happened elsewhere, this is something that's happening. But yeah.
Great. I think we can take 3 more questions. This question from Aman: what do you think about ZK Sync Solidity first approach versus pursuing Zinc, Cairo versus Solidity?
I think Cairo is a better approach. That's why we took it, because the constraints of generating proofs are better met by devising a new language that's catered towards that. But of course, that's one of the many differences in approaches that we have from other teams. Yeah, but I strongly believe we took the right approach.
Cool. Next question from Izat. Ali, this is about Cairo. Do you think it's possible to write an efficient Cairo code by transpiling existing Solidity code using warp? Or would it be very inefficient in terms of gas, performance, or readability, and it's better to learn Cairo?
This is one question I don't feel enough of an expert on, but I would definitely advise you to definitely spend some time learning Cairo. And I would advise to maybe dabble a bit. So write something simple in Solidity and try transpiling it and try writing it in Cairo, and decide for yourself which approach works better. I don't quite know. Yeah.
Right. I think the ecosystem is very dynamic and fluid, so I think we'll be coming back to these questions.
Actually, I wonder, I'm curious, what would you advise? Because I'm sure you're a far bigger expert than me on Cairo. So, Guilty Gyoza, what would you say?
Well, so I think I'm not in a good position to answer this because I do not have prior sort of buy-in into Solidity, the language. So there's no switching cost to me. I simply learn the native language and work with it. That's sort of our position. Yeah.
Mm-hmm.
Mm-hmm. Right. Okay, so let's do one more questions. And I think that the rest of the questions can go to our Discord. And I'm sure we'll find ways to answer all of it. So the final question is, what do you think about ZK Sync? Oh, sorry. That's the previous one. Final question is, do you have plan to provide privacy features at the protocol layer at some point?
I love this question. Okay. The scientist in me and the dreamer would like to see so many things. And I always say, I live in the future. Meaning, for me, like, yeah, sure, tomorrow we're adding that because we're going to need privacy. And you know what? It's not that hard, theoretically speaking, to turn the Stark proofs into ZK Stark proofs. Now, realistically speaking, it's a huge undertaking to add privacy correctly. By the way, adding ZK to the Stark proofs is very easy, but that's not enough. You need privacy preserving system, which means you need a whole tool chain to, I mean, you need to move to from an account-based system to one that is more like with, a Zcash style commitment trees and nullifier sets and things like that. And you need tooling for that. And that's going to take time. So my answer is, yes, we'll get there as a community, as the Starknet community, right? Once we open up things, then people who want privacy are going to start building this on their own, right? Without, doesn't matter what StarkWare decides. As often, this will take more time than I would hope or envision, and that's fine. So I just want to end by saying that I'm just elated to see the amount of attendance, adoption, intelligent questions, and passion for this new ecosystem that is forming. And again, mind you, this is something that the Topology team is really spearheading, without much of StarkWare's help, which is just beautiful to see. And this phenomena of grassroots developer movement embracing Starknet, which is just getting stronger and stronger, is just so beautiful to see. And I think this is a movement that will grow stronger. And those who are joining now and all of you attending are part of it, will really, really enjoy and benefit and contribute and be part of this journey. So on this happy note, I want to just thank Gilti Gyoza and Kunho, the Topology team, and all of you, and also for inviting me to speak here and just see this amazing energy out there. Yeah, go crush it.
Thank you, Eli and Gilti Gyoza and everyone coming here, especially 110 and 115 of you who came and listened. And thanks again for giving a wonderful talk for an hour. I think everyone is very much inspired and also wanting to learn more about the Starknet ecosystem. So as I said in the beginning, we will have a short office hour workshop tomorrow run by Owen's team. And I will be also posting a attendance form, Google form here, and also which is also posted on our Discord channel. So if you have attended, please feel free to fill those out. By next week, we'll do another session run by Henry from StarkWare, one of the awesome developer advocate, talking more about how to actually build things on Starknet. So I'm truly excited to have everyone, and thank you for your time again.
Kuno, I just want to ask if the questions can maybe just be copied and then posted on your Discord, and then if you can just let me and the StarkWare team try to answer some of them, because you see there are many good questions here.
Sure, I'll ask though. I mean, I'll post those on the channel, and then we should be able to have everyone answer and see the answers. Yeah, I'll do that.
Terrific. Thank you so much.
Thank you.
Thanks.
Okay, that'll be it. And thank you, everyone, and have a wonderful morning or afternoon or dinner. Night, everyone. Yep. Bye-bye.
Bye.